Hey everyone, here is the promised video on the divergence and curl of the magnetic field. This video is a lead into Ampere's law, but it's kind of the theory behind Ampere's law. And if something happens and you can't watch it right away, that's actually not a problem. And in fact, if we do lose power Monday through Wednesday or any subset thereof, this might not be the thing to spend time on. Ampere's law itself will be a higher priority, which if we do or don't have power, I'll either get that out to you as a video, as a asynchronous video like this one, or I will, if I can get onto campus to get power, if I don't have power, then I'll get you a live, we'll do a live Zoom video. So here it is, divergence and curl of B. So here I'll derive the divergence and curl of B, and I will start with the Biot-Savart law. So we have that the Biot-Savart law is B vector equals mu 0 over 4 pi times the integral of I dl prime vector cross r script r hat divided by script r squared. So just a quick picture to remind you, we need to know what all these r's are, all the r's are. So the primes go from the origin to the point inside the charge distribution. So the prime one is this one. So it goes, like we just said, from the origin to the point that you're interested in, which in this case is from the origin to the charge, piece of the charge, or in this case, piece of the current, which is my dl prime. And then the script r goes from that point to the point you're interested in. For a general, so I want to rewrite the Biot-Savart law. Instead of I want to write it for a general volume current density. So for a volume current density, we have that I is equal to the integral of j dot dA. And it's important, I'm keeping track, all of these, again, both the j and the dA would be in terms of the prime variables. And again, just drawing a picture, the prime variable goes from the origin to a point somewhere inside that. So now I'm drawing a thicker wire. And so the r prime goes from the origin to a point. It's hard to tell that's a prime, huh? From the origin to the point. I guess there's a separate prime there. To the point inside the j, which is the current density, the current as it's distributed throughout that. Looks like I've drawn like a thick wire. Right. Then using that, replacing I with j dot dA, I can write our Biot-Savart law like this. So I have that B vector equals mu 0 over 4 pi. Now there are two integrals there. There's the integral, there's a line integral, which was from the original Biot-Savart law. So the integral over the line, and then the integral over the surface. The integral over the surface came from the j dot dA. And so there's that, replaced I with j dot dA times the dl prime cross r hat that we had before, and all of that over script r squared. So now there are two integrals, and surface and volume, there's also a dA and a dl. J dot dA is a scalar. I'm going to go in order. I'm just going to rewrite this. I'm going to combine some of these things. That j dot dA is a scalar, but the j itself is in the same direction as dl. And then the last piece of the puzzle is that dA prime is times dl prime is the volume element. So area times length gives you the volume, so that becomes the volume element. And I can substitute that in and rewrite Biot-Savart one more time. B equals, I lost the B vector. It's certainly still a vector. B equals mu 0 over 4 pi times the integral j cross script r hat over script r squared times dv prime. And I just want to make sure and mention, I just want to go through all of those variables and make sure we know what is in terms of the primes and what is in terms of the unprimes. So the j is in terms of the prime, as we were just saying. We just redo that picture, the current density. And then the dv is in terms of the primes. And you might remember the scripty r. If you go back and look at that picture I had over on the left-hand side, the scripty r is vector r minus r prime. And then if you write that in components, just wants to write it out, x minus x prime, y minus y prime, z minus z prime, in my favorite column vector notation. And then one last thing in that, because we're going to take, as I said, today we're going to take the divergence in the curl, and it's important that the divergence, the del operator, is in terms of the unprimed r's. And let's see, I think I forgot to put that on the picture, but I will at some point add it. All right, so let's do the divergence of B. So divergence of B, that'll take us a little bit of math, and then we'll do the curl. So first divergence. So I'm just going to take the divergence of that whole thing. So both sides of the equation of the Biot-Savart law. So del dot B on the left, and then I can put the del inside the integral. So derivatives and integrals can move around each other. And so mu 0 over 4 pi times the integral of del dot, and then everything else inside the parentheses was there before. The j vector cross scripty r over scripty r squared. And then times the volume element, and again, that is with respect to the primes. And in order to evaluate that, we need a product rule. So I looked that one up for us. So we need a product rule, and so the generic form is we want a del dot, two vectors, A cross B. Those are both vectors, which looks like I missed the... Those are both vectors. Let's go ahead and add the arrows on top of A and on top of B. So del dot A and del dot B. Del dot A cross B, sorry about that, is what we're going to try to evaluate. Of course, we're going to substitute in our A and our B. So that's the next step. So instead of A and B, I have J and scripty R hat over scripty R squared. So using that, applying that product rule, I try to write them one right under the other. So if I let A be J and B be scripty R over scripty R squared, then del dot J cross scripty R hat over R squared equals scripty R hat over scripty R squared dotted into del cross J, that should be a cross J minus J dot del cross scripty R hat over R squared. All the derivatives of J turn out to equal 0 because this is part of why I was emphasizing that we have to pay so much attention to what is in terms of a prime and what is in terms of an unprimed variable. So the J is in terms of the primes, but the del is in terms of the unprimed. So if you take a derivative with respect to x of x prime, you'll get 0. Because when you take a partial derivative, you pretend everything else is a constant. So it turns out that that first term is 0, and we only have to deal with the second term. So on the next page, it doesn't show up very well. You'll have to remember, pause here if you need to. So on the next page, I'm going to show that it turns out that del cross scripty R hat over R squared is 0. We might actually have done that at some point. I was trying to remember if we had done that as an exercise before. So yes, I'm just going to evaluate that term. I'm just going to evaluate the del cross scripty R hat over scripty R squared. I always like to do this by components, and I write out the determinant of put the x hat, y hat, z hat in the top row. The del is partial x, then partial y in the y direction, partial z in the z direction. And I am writing a little shorthand here, so all of them have, I'm going to write our scripty R squared, R hat over scripty R squared is the same thing as scripty R vector over scripty R cubed. And so I'm going to use that. That's why that's why all these r cubeds are here. So I'm going to use that to rewrite, that's how where the x minus x prime comes from on the top, and then it turns into an r cubed on the bottom. So that's where each of those comes from. I am, if you can't sort of see it right away looking at it, it turns out, like I said, it turns out the whole thing's going to equal 0. So let's just look at one component, and I think you'll see by the symmetry of the components how it is that the whole thing turns out to be 0. So let's just look at the x component. So the way I usually do the determinant, the x hat component, this whole thing is the x hat component. You take I always think of like wiping out this row and that row, and then then I multiply this direction. So partial y of z minus z prime over r cubed, and then up this direction is how I usually think about doing my determinant. And that's where I get the partial y of z minus z prime over r cubed minus partial z y minus y prime over r cubed. So the fact that you have the partial y, but then you have the z primes already there, and then you have the partial z, but you have the y primes already there, is the symmetry that's going to make everything cancel out and go to 0. So if you look at my r cubed, it's that whole big quantity thing to the minus, if I flip it up to the numerator, it's to the minus 3/2 power. So when I take the derivative, that's where that minus 3/2 come from. And then taking the derivative of what's inside is where the 2 times the quantity y minus y prime comes from. So each one of them will have that because you're taking the derivative, because it's symmetric with respect to the x, y, and z components. And so as you can see from my writing, that whole thing just cancels out. You get the exact same thing on both sides, and you just get same thing minus same thing gives you 0. So indeed, that term, both of those terms, in fact, turned out to cancel out to 0. So that one's 0. Same cancellation for the y and the z components. Just by symmetry, it's totally symmetric. So that term, that del cross script r hat over script r squared equals 0, and that means the whole divergence of b is 0, because that was our last term. We already figured out the first term was 0 from our product rule, and that was the second term, and the second term was also 0. So the divergence of the magnetic field is 0. That makes a certain amount of sense. We know for a long straight wire, we figured out that the magnetic field wraps around the wire. But if you remember the pictures in Griffiths, the divergence, you can think of the divergence as spreading out from a point. So it doesn't really spread out from a point, it wraps around. So we do not expect the curl to be 0. Not surprising that the divergence is 0, but we would not expect the curl to be 0. All right, so let's do the curl. So the curl of B, I'm going to go back and start from the same place of the Biot-Savart law. So start from the same general form that we worked out with the J. So the magnetic field vector B is equal to mu 0 over 4 pi times the integral of J cross script dr hat over script dr squared dV. That V is the prime again. And now I'm going to take the curl of it. So I'm going to take the del cross both sides of the equation. So del cross B vector equals mu 0 over 4 pi. Again, I'm going to move the cross inside the integral. So integral of the curl of the quantity J cross script dr over dV. And again, this is another product rule that we need to look up. So this one's a lot longer. So the generic form of del cross the quantity vector A cross vector B equals A vector times del dot B minus B vector times del dot A plus B dot del of A minus A dot del of B. So all four of those terms, I'm going to go ahead and plug in. Same thing where I replace A with J and then B with script dr over r squared. So I'm just going to rewrite everything sort of right below so that we can see how it lines up. So del cross J cross script dr hat over r squared equals j times del dot r hat over r squared minus r hat over r squared times del dot j plus r hat over r squared times del dot j minus j dot del times r hat over r squared. That's a lot. But remember, we have that really great trick. We get to wipe out two of those right away because anything where you're taking the derivative of j is going to turn out to be 0 because of that primed unprimed thing. So the del's, both the del's in the two terms I just showed being crossed out. Anything where the del is in front of the j, so we're taking the derivative of the j, is going to be 0. And so both of those, both when it's the divergence and when it is just multiplied, that will end up being it's the same example again where you took the derivative with respect to unprimes, but the j's are all in terms of primes, and so all of those will turn out to be 0. So you get that those two middle terms are 0. Oh, then so this I started to write that then for that first term after the equal sign, the vector j del dot r hat over r squared, that is one that we worked out. If you remember, this was that weird special case for the divergence theorem where the left-hand side gives you one thing and the right-hand side gives you 0. And so we figured out that this was actually where we need a delta function. So that term, that first term right after the equal sign, becomes j, our current density, times 4 pi times the three-dimensional Dirac delta function of script r vector. So j times 4 pi Dirac delta function of script r vector. And we worked that out. In one of the in a couple of sections of chapter 1 that led into the Dirac delta function in chapter 1. Okay, we have one last term there on the end. I haven't dealt with the minus j vector dot del times the script r hat over script r squared. That's going to take just a little bit of math to work out. So the first thing we want to do is I want to actually rewrite instead of, so we just had this issue where when we take the derivative, everything's 0 because whether we're doing the primes or the unprimes. Well, at a later step in the problem, I'm going to want to use the divergence theorem, but I need them to be with respect to the same variable. So I'm going to do a swap where instead of doing del in terms of the unprimes, I would like to switch it so that it's the primes. And because I can only do this because I'm doing it on the script r vector. So I'll show an example of the x coordinate here. So the script r vector, as we already said, is regular r vector minus r prime vector. So if I just show an example of just what I mean, how this works by just considering the x components, the regular del is the partial x, and then you're operating on x minus x prime. And then that's the exact same thing as putting a minus sign in front of the derivative with respect to x prime of x minus x prime. Because the script r is r minus r prime, the primes have the minus sign with them, so that if we just replace del with minus del in terms of the primes, then it will be the same thing. So I'm going to swap, so I'm going to give a new notation of a del operator with a prime on it, which means what we were just talking about. So I'm just going to switch the variable. So I can rewrite that last term, minus j dot del times script r over script r squared is now equal to plus j dot del prime. So that means derivatives with respect to the primes instead of the unprimes, r hat over r squared. The usual r hat over r squared. So let's, again, just consider one component at a time. So that whole thing is a big vector mess. So let's just look at the x component. So just the x component of that term becomes j dot del times x minus x prime over script r squared. We need another product rule. This is, what's that, the third one so far? So another product rule. This one is a scalar times a vector. So because I've taken just the component, so I'm only working in the x component, the x minus x prime over script r squared is like the f. So del dot a scalar f times a vector equals f times del dot a plus a dot the gradient of f. So again, just, I only want, it's hard to recognize, the j becomes the a. So if you look at that last term, it's actually that last term that I want. So I'm just going to rewrite the product rule as the difference there, so that I'm solving for that a dot del f term equals the whole thing, the product rule part, the del dot f times a minus f del dot a. So that term is the one that like I said, I'm going to replace j with a and del with del and f with that x minus x prime over r squared thing. Let me just write that. So trying to write it right underneath, but it takes up a bit more space. So j dot del prime times x minus x prime over script r squared equals del prime dot the quantity x minus x prime over script r squared times j vector minus x minus x prime over script r squared quantity del prime dot j. All right, so that's my product rule. And remember, this is just the x component of this one term. That last term, that del dot j, hopefully that looks familiar. We did that very recently. That's the continuity equation. So recall that the continuity equation, we derived del dot j equals minus the partial derivative of rho with respect to t. The fact that we have the primes here again is good, because remember the j is in fact in terms of primes. So this is not one of those where it's going to be 0. So this is one where it's 0 because the del dot j is really minus partial rho partial t. But for magnetostatics, which is what we're doing right now, for steady state currents, there is no time derivative of rho. Remember, rho is the charge density. So if the current's a constant, that will also be 0. Then rho would be a constant, is what that means. And so therefore it would be 0. All right. So we just figured out that second term of the product rule of this term will be 0. And we have to do a little work for the one remaining term that we have left. So we still have one term left, and it is, and so, yeah, so we basically have, let's see, I'll write in some color that I can erase. We basically have this term left. So we haven't dealt with, there's one term that we haven't dealt with. The others weren't all 0. Remember, that was that direct delta function one. So we haven't wiped them out yet, but I'm going to collect them all here in a minute. So a little bit more math to figure out that the integral of this term does in fact go to 0. But we have to actually recall that this came from the Biot-Savart law, which we ended up, when we replaced I with j, we were able to write it as a volume integral. So remember that this term is under a volume integral. So I'm just going to rewrite that. So recall that this is under a volume integral. And it came from the fourth term on the previous page. So the integral of del prime dot x minus x prime over script r squared j. So that's just repeating this term right now. That's where the purple arrow goes. And then I'm putting it back under the volume integral. So the integral of that term dv prime, again, the integral was always over the prime variables. I want to use the divergence theorem, and this is what I was saying when I made that swap from del to del prime. This is why, because I can't use the divergence theorem unless the variables that I'm using on both sides of the divergence theorem are the same. So if I apply the divergence theorem, that's what I just said about the variables. That's why I swapped the variables from del to del prime, so that they matched when I used the divergence theorem. So recall that the divergence theorem takes the del dot a vector over a volume integral and turns it into the closed integral over the surface of the same vector. So that a vector in this case is the x minus x prime over script r squared times j vector. That's all of our vector A, if you're looking at the divergence theorem, dotted into dA prime. So again, the primes all should match. So now this is a surface integral, but the cool thing is that I can pick my surface, and there's no particular reason, and Griffith says we've done this before in other cases, we can expand this surface that we're integrating over. We can basically integrate over all space. There's no harm in it. J is 0 anywhere outside the wire, and so if we just choose the volume anywhere outside the wire, that integral is going to evaluate to 0 because all the J is safely inside the volume. So if we just pick a volume where J does not cross the boundary, then the integral, this closed integral over the surface of the boundary surface, is going to be 0. So that term only goes away when we consider the integral of it. So it's not the term itself that goes away, but it's the integral of that term because the J doesn't cross the boundary. We pick a volume such that all the J is safely closed inside. All right, I have all these pieces here. I'm just going to summarize this really quick because that got very, very long. So let me just pull all those steps in. It's also across a different page, which makes it really hard to see on this particular program. So let me summarize this. So we started off with our del cross B, where we just took the Biot-Savart law, and I did del cross both sides. I got that. So del cross B is mu 0 over 4 pi times the integral of the curl of J cross script dr hat over script dr squared dv. That one is also the prime. I drop primes really easily. Then I looked up the product rule, and we ended up getting mu 0 over 4 pi times the integral J times the quantity del dot script dr over script dr squared dv prime, and then minus mu 0 over 4 pi J dot del script dr over script dr squared dv. Sorry, that's a little bit cut off. That second term is what we just spent all this time. We just finished proving that everything in that second term is what integrates to 0. So that was what we just did the divergence theorem of and figured out that that term goes away to 0. The first term was back on the previous page. The first term is the one where we figured out that thing inside the parentheses was equal to 4 pi times the Dirac delta function. Okay, so we replace that term with the 4 pi times the Dirac delta function, and we get that our del cross B on the left-hand side equals mu 0 over 4 pi J vector 4 pi Dirac delta function in 3 dimensions of script dr vector dv prime. So remember how the delta functions work. So we're integrating so that script dr is like r minus r prime. The volume integrals are over prime. So remember that the delta function is the infinite spike right where, in this case, where the value inside the delta function is 0. So that's right where r equals r prime. So J, which was a function of r prime, will become a function of r, and the 4 pi is left, and the J is left, and that's it. Everything else, the delta function wipes out everything else except the value of J right at r. So we get mu 0 over 4 pi times J of r, no longer r prime. All the r primes are gone. We integrated them all the way in that step. And then times the 4 pi, which came along from the Dirac delta function. 4 pi's cancel, and I'm just left with mu 0 J. Cool. So it turns out that the curl of the magnetic field is mu 0 times J. That is a great result, and it is, in fact, Ampere's law in differential form. So I just derived the differential form of Ampere's law, which is not the most useful form in terms of doing the problems, but it is still very true, and it turns out to be it turns out to be the magnetostatic piece of one of Maxwell's equations. There will be a term, you remember the changing flux with respect to time, so there will be some fixes to this later when we allow the current to move, or to change. So del cross B equals mu 0 times J, and the divergence of B, del dot B, is 0. And this one, like I said, the curl, this is Ampere's law in differential form. And next time, in the next video, I will, or in class, whichever happens, depending on the power, and then in the next video or session, we will work out the integral form of Ampere's law, which is, like Gauss's law, the more useful in terms of helping you solve problems. You want the integral form. So, Ampere's law next time.